So let's think about the lossless version of the 1 degree freedom revolute vector field. We would like to write a vector field, namely we want to rewrite our second order scalar ODE as a first order vector ODE. But this time we're going to get a nonlinear vector field. There can't be any matrices. There are no matrices in sight because it's a nonlinear function. And not only that, because it's a nonlinear differential equation, there won't be any closed form series that we know how to write down, okay? And so the role of the theory is going to guarantee that the flow exists, that that infinite series exists, even though we can't write it down. And it's going to give us rigorous methods for reasoning qualitatively. We're not going to have closed form expressions usually. We might get some closed form approximations, but we won't get closed form expressions without approximating. We'll have to be reasoning qualitatively about them in order to get formally guaranteed properties. Remember from the linear case how we went from the acceleration field c of the tangent vector. In that case it was xx dot. Now it's going to be theta theta dot. So we had theta double dot is balanced by this acceleration field. I'm now going to write it down as q having theta and theta dot in it, and therefore q dot has theta dot and theta double dot in it. And so theta double dot, it's just saying theta dot is equal to theta dot, and theta double dot is equal to c sub r. But I now get to think about this as a vector field in 2 dimensions, right? It's a vector field that takes this 2-dimensional quantity theta theta dot and gives me back a 2-dimensional vector f at theta theta dot. That's the way we like to think about our dynamical systems. And you'll remember that in this case, because the vector field is nonlinear, not only don't I have a matrix, I don't know how to write down in closed form the infinite series solution that I get for the flow induced by this vector field. Now, I can deduce that I will have a flow, that I'll get a certain kind of uniqueness and existence of solutions, but I don't know how to write it down in closed form as a function of time. I'd like you to compare these equations that we just developed to the analogous equations in the previous segment. In that case, we had closed form infinite series expression of a time parameterized family of invertible nonlinear functions. But now I'm getting guaranteed existence of a time parameterized family of invertible nonlinear functions that I otherwise can't write down. So please go back and try to review how this situation is similar conceptually and in terms of mathematical guarantees, but not in terms of closed form expressions. A lossless mechanism conserves energy, and that's the thing which is going to help us. We won't be able to write down the trajectories, the solutions, but we will be able to write down the orbits because of conservation of energy. And it's the orbits in closed form that are going to turn out to be crucial in later weeks. So let's once again examine the power, which is the energy change along the trajectory of the total energy, and the vector field. And we're going to remember that the change in energy, just as energy is a function of power, so it is that the change, just as the energy is a function of the state, so it is that the power, which is the d by dt of that energy, turns out to be a function of state. We're going to conclude that because there's no power dissipation, energy is conserved in the case of no damping. We better get that result. And also we're going to get, for the damped harmonic oscillator, we're going to get that the power vanishes. Let's do that computation. d by dt of total energy uses the chain rule. D by t of this composition of the total energy expressed along the trajectory is gotten by taking d by q of the total energy times d by dt of the flow through the initial condition q0. d by dq of total energy we've seen is just d with respect to theta of the potential energy because there's no theta dependence in kinetic, and d with respect to theta dot of the kinetic energy because there's no theta dot dependence in phi. Moreover, because the flow satisfies the differential equation, d by dt at wherever we are from q0 is f evaluated at that wherever we are from q0. Well, what is that? I should plug this wherever we are into the vector field, and out will come theta dot at that time t and see the acceleration field evaluated at that theta at that time t. And that's all inner producting with the force law, because we remember that the force field is the negative Jacobian of the potential energy, and the kinetic energy gradient. Kinetic energy gradient we've evaluated before. The vector field we've talked about before. And so I think you'll see that when you take this inner product of negative phi times theta dot plus ml squared over ml squared times phi times theta dot, I just get a cancellation and I get 0, which is another way of saying that the total energy is conserved. And once again, I invite you to compare this with the power computation from the linear time invariant system. This is an example of a qualitative method, a rigorous conclusion from, of a qualitative kind. We've concluded that energy is conserved. And the importance of this is that we can solve the constraint equation in closed form, not with respect to time, but we can trade velocity for position and thereby get the orbit in space of where this thing is, okay? We can get the velocity, q dot, theta dot, as a function of angle theta and as a function of initial condition and the energy at the initial condition. We can't get the trajectory in time in closed form. We can get it as an integral. This is an integrable system, but the integral will be what's called an elliptic integral, and it won't have a closed form expression. But we can get the trajectory. So we can't get the time trajectory, but we can get the orbit or the position. The flow has no closed form expression, but we will get the orbit, the geometric curve on which this trajectory is lie. So we're getting these black and red curves algebraically from conservation of energy. Let's just see how that works. We know that whatever initial condition we started in, the total energy is conserved. Let's call that total energy E sub 0. The total energy along the trajectory, even though we can't get what that trajectory is, has to constantly be equal to E0, the initial energy, because energy is conserved. Let me therefore solve at any time. I don't know what time it is. Let me not care about time. At whatever time it is, because the position angle theta and the velocity theta dot have this relationship, I can solve this equation for the theta dot, and you can see that I can get theta dot as a function of knowing what the initial energy was and knowing what angle we're at. And this way of using the orbits to get closed form information about these trajectories, which I can't otherwise get as time functions, is going to be hugely important in certainly in week 6, but particularly in weeks 8 and weeks 9 when we get there later on in the course. So please make sure that you're understanding how I got these orbit closed form expressions for the orbit, even though the flow had no closed form expression at all. I'm now just playing back for you finally to remind you that this orbit picture that you see in the yellow phase plane, theta and theta dot, I'm hoping that you're associating that in your mind with the time trajectories as they spin out. And these time trajectories as they spin out are the things that give us these orbits that Wei Shi is plotting in the right-hand side extreme of this figure. I'm hoping that you're keeping these all in mind at the same time as we talk in these terms. As we move ahead, I'm hoping that you're going to be remembering that these geometric techniques, which we can see completely in 1 or 2 dimensions, still continue to work in high dimensions, and they become very, very important. They're usually more complicated, and they will get very complicated in weeks 8. Week 6 is sort of an intermediate week. They will get very complicated in weeks 8 and weeks 9, but as the state space of the dimension of the state space grows, the very nature of these ideas is that they generalize, and they can become very, very, very powerful for us way up in the higher dimension.